Design and buckling analysis of connecting rod. Abstract connecting rod plays a crucial role in the working of an IC engine, whose key role is to transmit power from the piston pin to the crank pin. It basically acts as a rigid link and transmits the reciprocating motion of the piston to the rotational motion of the crankshaft. It is a slender part with its length considerably greater than its width. It is mainly subjected to axial compressive stress. In this paper, we have considered a 4-stroke single-cylinder IC engine of 66 mm bore diameter and 99 mm stroke length, and calculated the required dimensions. We have modeled the connecting rod using SOLIDWORKS software, and carried out static and buckling analysis in ANSYS software. Keywords: connecting rod, IC engine, finite element analysis, static structural, buckling analysis, ANSYS. Introduction. Connecting rod is vital component for the basic working of IC engines. It connects the piston and the crankshaft together and helps to convert the reciprocating motion of the piston into rotational motion of the crankshaft. It also transfers oil from crank pin to piston pin for lubrication. Its key is that it should have the capability to withstand the compressive stresses from the maximum gas pressure on the piston crown and the inertia force of the reciprocating parts, as well as buckling and fatigue stresses. 3, 4, 5. The connecting rod is generally made from materials like medium carbon steels or alloy steels. The carbon content varies from 0.35 to 0.45% in medium carbon steels. Typically, nickel chromium or chromium molybdenum steels are used as alloy steels. The connecting rod is usually manufactured by the drop forging process, casting process, and powdered metallurgy. 1. The performance and lifespan of connecting rod is affected by numerous factors and design parameters. These factors include the type of engine to be used, maximum speed and torque that the engine can generate, shank cross-section like I-section and H-section. Design parameters include thickness of shank, radius of fillet, criteria for material selection, manufacturing processes used, etc. By improving these aspects, we can increase the performance of connecting rods. 6, 7. Connecting rods are widely employed in range of engines such as single-cylinder engines, multi-cylinder inline engines, V-engine, radial engine, opposed cylinder engine and opposed piston engines. A connecting rod has 3 parts, a small end, a shank section, and a big end. They can be produced as single-piece or 2-piece components. To ensure that the bearings would fit properly, the piston pin end and crank pin end pinholes are machined as parallel holes. The piston and the connecting rod are coupled at the small end by the piston pin. The small end of the connecting rod will have a solid bushing of phosphor bronze or an analogous material. As the big end revolves with the crankshaft, the small end is forced to swivel on the piston pin. The bushing is necessary due to the high pressure and temperatures, in spite of only a slight movement relative to the piston pin. A 2-piece con rod is made up of 2 parts to enable it to be clamped around the crank pin. The bottom part, or rod cap, is made of identical material as the rod and is fastened to the con rod by 2 bolts. The surface that is in contact with the crank pin is generally a split shell bearing. The 2 parts of the bearing are positioned in between the small end and crank pin by dowel pins. From the perspective of functionality, connecting rods must have the required rigidity at the lowest possible weight. 8. 2. Analytical design. Figure 5. Isometric view of con rod. 4. Finite element analysis of connecting rod. Using ANSYS geometry design modeler, the small end was sliced into 2 equal parts. This was done so that the force would be applied only to the lower half of the small end, similar to actual conditions. It can be seen in Fig 6. Below. I-meshing. Tetrahedron geometry was used for the meshing. The element type was TET1010 noted tetrahedron. Mesh refinement was carried out at the locations as per the structural error plot was showing significant error. Dynamic behavior is observed for both, the small end and big end of the connecting rod. The small end moves along with the piston pin, whereas the big end moves with the crank pin. Hence, remote displacement has been applied to both the ends. Condition given to the big end is free rotation about y-axis as it rotates with the crank pin. Condition given to small end is free translation along z-axis and free rotation about y-axis. Therefore, the connecting rod behaves as if the small end and the big end are hinged at the piston pin and crank pin respectively. 3. Static structural. 4. Buckling analysis. The eigenvalue buckling analysis system in ANSYS was used for the estimation of buckling modes, see Fig 13.a, 13.b, 14.a, 14.b. It is a linear buckling analysis method. The buckling load has been evaluated by taking the product of applied load and load multiplier. The buckling analysis was done for 2 modes. The results generated by ANSYS for both the modes resembled the real-world scenario of failure of connecting rod, i.e., the first and second mode of buckling are exactly alike to the buckling failure of connecting rod. See Fig 13a, 14a. 8. For calculating the theoretical buckling load, the force acting on the small end was multiplied by factor of safety. The load multiplier which we get from buckling analysis in ANSYS is nothing but the factor of safety. So, for calculating the analytical buckling load, we need to multiply the force applied by the load multiplier. Load multiplier was 3.0178 for mode 1, see Fig 13.b, and 6.6396 for mode 2, see Fig 14a. 6. Conclusions. In this study, we have designed the connecting rod, carried out finite element analysis for connecting rod, and the results have been tabulated in the previous sections. The following inferences can be drawn from finite element analysis. Static analysis shows that the stress generated in the model is within acceptable limits or maximum allowable stress. The displacement plot shows very insignificant deformation, which has no consequence on the functioning of the connecting rod. Hence, it will not deform under the applied load. Buckling analysis shows the buckling shape accurately, with the maximum deformation in the center part of the connecting rod. Buckling analysis gives buckling factor greater than 1 and hence the connecting rod will not buckle under currently applied load. The values of theoretical factor of safety and analytical load multiplier are almost identical. From the load multiplier we can conclude that the connecting rod can withstand up to 3 times the current load without buckling. Thus, it can be concluded that the design and analysis of the connecting rod was carried out both accurately and successfully.